Periodic trends will be the topic of this lesson, and we're specifically going to look at 3 periodic trends. We're going to look at atomic radius, ionization energy, and electron affinity. Now for atomic radius, we are going to find out that francium over here is the fattest element on the periodic table. And then we're going to find out that ionization energy, the energy it costs to remove an electron, is going to follow the exact opposite trend up towards helium. We'll find out that the smaller elements require more energy to remove that electron. And finally, we'll talk about electron affinity, which is the exact opposite of ionization energy. So electron affinity is the energy change associated with gaining an electron. And we'll find out that in general, it increases going left to right across the periodic table. And when we say increases, though, we got to be careful on electron affinity, because when we say increases left to right, we mean it gets more negative going left to right, that it's a bigger release of energy when an atom gains an electron. Now, we're going to go through the reasons behind each of these trends. We're going to go through the numerous exceptions that you're on the hook for with each of these trends. And we're going to look at a variety of cases that you are going to be required to apply these lovely trends as well. Now, this lesson is part of my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notification. You'll be notified every time I post a new lesson. All right, so let's start with atomic radius here. And once again, we said that francium is the fattest element on the periodic table, and why not? If you spend too much time in France, you're going to eat too much bread and cheese and eclairs and drink too much wine, and you're going to get fat just like francium. Now, this is going to involve 2 trends here. So we've got a vertical trend and a horizontal trend, and the vertical one is the easier one to understand. It's fairly intuitive. So the atomic radius, which is the size of the electron cloud, essentially, gets bigger as we go down the periodic table. And we can kind of, pretty intuitively see why that is. As you go down the periodic table, you just get a new shell of electrons every time you move down. And so you just get more shells of electrons. And so, yeah, if you get more shells of electrons, then your electron cloud should get bigger. And that's not the one we struggle to understand, but the horizontal trend, this is the one that's a little bit of a pain in the butt, and that initially seems counterintuitive. But your atomic radius, the size of your electron cloud, is going to get bigger going to the left. And notice this is exactly in opposition to our typical trend for atomic mass. Atomic mass actually increases going to the right generally. So how do we explain this? Well, first off, note that they don't have to correlate, because most of the mass of an atom is concentrated in the nucleus. So how heavy the nucleus is doesn't necessarily have to follow the same trend of how big is the electron cloud that's around the nucleus. So let's just kind of divorce those and just show that maybe they don't have to be the same, because they obviously aren't in this case. But it turns out it's going to come down to what we call effective nuclear charge. And let's take a look at, here we've got, the period 3 elements, sodium all the way over to argon. And we can see that, yep, as you go right to left, they definitely get bigger. So now let's talk about this effective nuclear charge, what exactly is, how we calculate it, and how we can use it to explain this horizontal trend. So if we look at effective nuclear charge, it really is an idea of, focusing on those outermost electrons. So focus on those, and how attracted to the nucleus are they? Because we got an issue. They're attracted to the nucleus because they're negative, and the nucleus is positive, but they're also repelled by all the other core electrons that are closer to the nucleus than they are. So let's take a look at sodium, for instance. And here I've got sodium's nucleus kind of diagrammed in the middle of this lovely Bohr model of the atom. We're going to make use of that Bohr model. Again, I know it's wrong, but we're going to use it. It is useful in places, and this is one of them. And in the case of sodium, sodium's atomic number 11. And so we're going to have a plus 11 charge on our nucleus, 11 protons in there. And sodium is going to be 1s2, 2s2, 2p6, and let's work that out. So 1s2, 2s2, 2p6, 3s1. And so we've got 1s2. We can look at that as being, let's do this in red. So we got electrons in the first shell. There's 2 of them. That's the 1s2. Then we got 2s2, 2p6, a total of 8 electrons in the second shell. So 1, 2, 3, 4, 5, 6, 7, 8. And then finally 3s1, we've got 1 electron in the outermost shell. And notice he's the outermost shell. He determines the outermost boundary. So essentially from the nucleus to him, that's the atomic radius. And so it comes down to all about him. And he looks at that nucleus and says, I'm attracted to you. But then he sees all these electrons that are closer to the nucleus, that are between him and the nucleus, and he's like, I'm repelled by all of you. And the effective nuclear charge is going to be the balance between those two. And we've got a lovely formula for calculating it. We say that our effective nuclear charge, Z here stands for that charge, and I can spell here, EFF, effective nuclear charge, is going to equal the nuclear charge Z, which in sodium's case would be plus 11, minus S here, which stands for either the shielding or screening electrons, however you want to look at that. And if you're the valence electron, those shielding or screening electrons are all the core electrons. They're closer to the nucleus than you are. And so in this case, in the case of sodium, we'd have plus 11 minus all 10 of these core electrons, these 2 and the 1s, and then the 8 and the 2s and 2p, so there's a total of 10 shielding or screening electrons. And we see that for the case of sodium, his effective nuclear charge is going to be plus 1. The more positive this number is, the greater the attraction to the nucleus, the closer it's going to get pulled in. The less positive this number is for effective nuclear charge, then the less attracted those valence electrons are to the nucleus, and the less they're going to be pulled in, so it'll be larger. So this is kind of what we're going to use here. So if we move over to magnesium for a second, well, magnesium is atomic number 12. Okay, so magnesium's no longer got a plus 11 charge on its nucleus. It's going to be plus 12. Okay, this part of the calculation becomes plus 12. So, and we're also going to gain an electron out in that third shell, so 3s2. So when you start putting electrons in that outermost shell, they like to stay as far apart as possible, especially when they're in the s orbital. They generally spend the majority of their time as far away as possible. And so the approximation we make is that the electrons that are in that valence shell don't really affect each other to any significant degree. And technically it's not 100% true, but it's it's just true as some of the other approximations we make in this regard. So, but the truth is this: when this electron looks at the nucleus, it says, I'm attracted to you. But when it does look at that electron, it says, I'm repelled from you. And so the truth is, it actually, even though it's on the other side of it, still repels it away from the nucleus to some small extent. So it's not a 100%, not 100% accurate here to kind of ignore all the rest of the valence electrons. But to a rough approximation, it's not so bad. So we're only going to, on this screening or shielding electrons, count the core electrons. We don't count anymore. And so as we went from sodium to magnesium, we got one more positive charge on the nucleus and plugged that in for Z, but we gained more valence electrons, but we didn't gain any more core electrons, and so the screening electron value doesn't change. And so now we've got 12 minus 10, and so for magnesium here, we're going to see plus 2. Let's do one more, move on to aluminum here. Aluminum is atomic number 13. So now the nucleus for aluminum is going to have a plus 13 charge. We'll substitute that in right here as well. And we're going to add one more electron, so 3s2 and 3p1. So we'll add one more electron into that outermost shell. So, but once again, we haven't added any more core electrons, any more screening electrons. And so we're now going to have 13 minus 10. And so for aluminum, plus 3. And if we did this for all of them all the way across, our effective nuclear charge would just keep increasing one by one by one, because we keep adding a proton to the nucleus to increase that nuclear charge, but we're not adding any more core electrons, only valence, and so this S number is not changing. Cool, and so as you can see, the effective nuclear charge felt by those valence electrons increases as we go left to right. And again, it's a measure of how attracted those outermost electrons are to the nucleus. And so argon's like, my outermost electrons are most attracted to the nucleus, and that's why he's the smallest. It pulls him in the tightest. And so in this case, we see that effective nuclear charge here increases left to right on the periodic table, and that's how we ultimately explain that atomic radius increases the opposite direction. Cool, this is our trend for atomic radius. And again, you do need to understand that it's in terms of effective nuclear charge, that they work in opposing directions on the horizontal. So you should also realize, though, that in the vertical, there's no difference. So it turns out all the alkali metals, the valence electron has an effective nuclear charge of plus 1. For alkaline earth metals, plus 2. So boron's column, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. Notice I didn't point at helium because he's only plus 2, but the rest of the noble gas is plus 8. And that's the way it works. It turns out that effective nuclear charge felt by the valence electrons happens to correspond to the number of valence electrons, but it was that Z minus S formula that we used to kind of calculate it. So now that we understand this trend for atomic radius, there's a few different places where we might have to apply this. So in the first here is just simply, you might have to just compare them directly. I'm going to leave it on the hook that you can do that now that we know the general trend, that as we move down towards francium and to the left towards francium, the atomic radius increases. Okay, so but the other place you might have to apply this is on bond length. So if you look at two atoms bonded to each other, so the distance from nucleus to nucleus is what we actually define as the bond length. And if you notice, that just happens to be the sum of the radius of one atom plus the radius of the other atom. And this is why it's totally related to atomic radius. You're just adding up the two atoms' atomic radii to get there. Now that's how you do it if it's a covalent bond. It turns out if it's an ionic bond, you'd actually end up with their ionic radii. But the truth is, and we'll talk about ionic radii here in a little bit, they don't end up being that different in your calculation either way. Again, for covalent bonds, you really should use atomic radii for neutral atoms, and for ionic bonds, you should really use ionic radii. But the truth is, you're going to be fairly approximately correct in either case, even if you mistakenly use the wrong one. But if you know what you're doing, you should use the proper one. We'll talk about ionic radii here in a little bit. So if I give you a bunch of different bonds, like let's say I give you a carbon-fluorine bond, carbon-chlorine bond, carbon-bromine bond, and a carbon-iodine bond, and I say which of these is the largest bond, or which of these is the smallest bond, or rank them, or something along those lines. So let's just go which is the longest bond in this case. Well, notice I gave you a nice comparison. The carbon is the same in every case, so then it really is just going to come down to the other atom. Whichever one has the biggest other atom, the atom with the largest atomic radius, is therefore going to have the longest bond. And we see fluorine, chlorine, bromine, iodine are the halogens right here and getting bigger as you go down. So the bond to iodine would end up being the longest. The bond to fluorine would end up being the shortest. So this is how we apply atomic radius to bond length. All right, so let's now talk about ionic radii, and we're going to treat cations and anions separately. So again, cations are positive ions, anions are negative ions. And I've got here listed both the atomic radii for the neutral species, kind of already encircled there, and we're going to compare those to the corresponding ionic radii. Now, one thing you should realize and remember is that metals tend to lose electrons and form cations. Non-metals tend to gain electrons and form anions. So, for example, potassium, being an alkali metal, we should expect his most common ion to be +1, calcium's most common ion to be +2. On the anion side, they tend to gain electrons to look like a noble gas. So chlorine typically is going to be -1. Most common ion for sulfur is -2, both in an attempt again to get a filled octet and look like a noble gas. All right, so if we look at the difference between potassium and potassium +1, so for potassium to end up with a +1 charge, it has to lose an electron, a single electron. But in this case, if you look at potassium, potassium has one valence electron. So when you lose one electron, you actually lose the entire valence shell, the entire outermost shell. And so as a result, you end up seeing a very significant decrease in size. You can see here we're going from 243 picometers down to 133 picometers, a big, significant reduction in size. And so just put the numbers on there. They're not important as far as the actual values. What I did want you to see is that this reduction in size is very significant. It's not just like, it goes down a couple percent. No, it goes down a huge amount in comparison. Same thing with calcium here. Lose 2 electrons, which again would lose the entire valence shell, go from 194 picometers all the way down to 99 picometers. A very significant, almost pretty much cut in half, essentially, its size. Now, anions, on the other hand, instead of losing electrons, we're going to be gaining electrons in the electron cloud. And if you gain a bunch of electrons in the electron cloud, or even just one, all of a sudden now with more electrons, they all repel each other a little more away from the nucleus, making the size increase. And again, I only show sizes on here so you can see that it's a rather significant increase. In this case, sulfur is going to gain 2 electrons, and when he does, he more than doubles in size, going from 88 picometers to 184 picometers. In chlorine's case, going from 79 picometers when he gains 1 electron to become a chloride ion to 181, also a more than doubling in size. So significant increases in size when we either lose electrons and become cations, or when we gain electrons and become anions. Now, a couple places this could show up on the exam. You might see, which of the following has an atomic radius, which means neutral atom, has an atomic radius that is larger than the ionic radius. Well, if your atomic is larger than your ionic, then we're talking about something that forms cations, which means pick a metal. On the other hand, if I said, pick for me an element in the answer choices that has an atomic radius that is smaller than the ionic radius, well, if the ionic radius is bigger, that means we're forming anions. And so if you want to pick an element whose atomic radius is smaller than the ionic radius, you need to pick a non-metal from this region on the periodic table. One other thing you should note is if we start comparing a bunch of different ions, we're going to run into a problem. It's easy to compare an atomic radius to a corresponding ionic radius. So because we know it's either going to be bigger or smaller based on whether we have cations or anions. But what if we just start comparing a bunch of different ions of different charges? Well, we're really limited on the comparisons we can make. So like, let's say I gave you, let's just pick some of the period 2 elements. Let's say I gave you magnesium, calcium, strontium, barium. And I said, which one is the biggest? Well, these are all neutral atoms, so this is just the atomic radius trend, and it increases going down, so we should expect barium to be the biggest. No big deal. Okay, what if all of a sudden I did this? And just for barium and only barium, I gave you a barium ion. So now I want you to compare the atomic radii of magnesium, calcium, strontium to the ionic radii of barium. Well, that's not a comparison we're really equipped to make. I mean, if you did know that barium's radius, there's a significant decrease, then you might still think that strontium is the biggest, but it's not really a comparison you're going to be asked. We don't view it as being fair. Now, one thing we could do here is we could just make them all +2. And if they're all the same charge, well, then they all, in this case, being cations, all went through a big decrease in size. And so whoever started out the biggest is probably going to be the biggest at the end, and we'd still pick barium 2+. So as long as they all have the same charge, you can just follow the atomic radius trend, and life is good. And that's a fair comparison. So there's only one instance where we'd actually start giving you things with different charges and expect you to be able to make the comparison. Let's take a look. So the only comparison we're going to give you where you're comparing things of different charges is likely to be an isoelectronic series. Now, if you don't know, iso, that prefix means the same. And an isoelectronic series is a series of elements or ions that all have the same electron configuration, the same overall number of electrons in this case. And so it turns out all of these are isoelectronic with argon. They're going to have 18 total electrons just like argon. Sulfur, notice with atomic number 16, with a -2 charge means gain 2 electrons and end up looking just like argon. Chlorine gains 1 electron to have 18 electrons. Potassium loses an electron to look like argon and have 18 electrons. Calcium loses 2 electrons to drop down from 20 and look like argon. So these all have the same electrons in their electron cloud. The question really becomes, which one is most attracted to its nucleus? Which one is least attracted to its nucleus? Well, if we look at the atomic numbers here, so here we've got atomic number 16, 17, 18, 19, and 20, and that corresponds to the number of protons in the nucleus. And so if I said which nucleus is the most positively charged, you'd say calcium's is. It's got 20 protons in it. As compared to sulfur's over here, it's only got 16 protons in it. And since they all have the same electrons in the electron cloud, this one's got the most positively charged nucleus for calcium, and therefore it's going to attract those electrons in the tightest and therefore end up being the smallest. And so when you've got an isoelectronic series, it's all about how attractive, how positively charged that nucleus is. And so the most positively charged ion in your series is going to be the smallest because it's got the most protons in its nucleus. And therefore the most negative one would be the largest. And I can put these in order. So just as they go from negative to positive, they're going to get smaller and smaller and smaller and smaller in our lovely isoelectronic series. All right, we're going to move on to talking about the last two trends. We're going to kind of talk about them in parallel since they're related to each other. They're opposites, it turns out. So we've got ionization energy and electron affinity. And ionization energy is the energy required to remove an electron from an atom, whereas electron affinity, think of affinity meaning like loving electrons. So electron affinity is the energy change associated with gaining an electron. So it usually costs energy to remove an electron from an atom. That electron is part of that atom because it's attracted to the nucleus. So if you want to pull it away from the nucleus, pull it off that atom, it's going to cost you energy. So, but we see this is what it looks like. It turns out that ionization energy and electron affinity, the last part of the definition here is that they're both defined for atoms in the gas phase. It's part of the definition here. And so I can see that if I'm going to lose an electron, ionization energy, that boron would go to a +1 charge and the electron that was lost would be a product. Whereas on the other hand, if I do the electron affinity of oxygen here, so oxygen's going to gain an electron. Electron is a reactant when it's gained, and it results in a negative charge instead. So that's kind of the difference. Now, if it costs energy to remove an electron, then usually we're actually going to release energy to gain one. So you don't have to like push an electron towards an atom. It wants to typically go to that atom. It's like, you want me to be close to that nucleus over there? That's where I want to be. So these are usually negative values. Now we'll see exceptions with both trends, but that's kind of the general idea. So ionization energies are positive because it costs energy to remove an electron. Electron affinities tend to be negative because you typically release energy when you gain an electron. All right, so we'll start with the general trend for ionization energy, and it is exactly the opposite of atomic radius. So if we look, so if you want to remove an electron from an atom, then the smaller the atom, the closer its electrons to the nucleus, and the harder they're going to be removed because they get a greater attraction to the nucleus. And so if atomic radius increased all the way down here to francium, then we shouldn't be surprised if ionization energy is going to increase in exactly the opposite fashion. So as you go up a group, ionization energies increase because you're getting smaller and smaller atoms, and that's going to be harder to remove those electrons because they're more attracted to the nucleus. Same thing as you go across a period. As you go across a period, your effective nuclear charge is increasing and they're getting smaller, both of which explain the reason why your ionization energy is going to increase and it's going to cost more energy to remove an electron. Now, in the case of electron affinity, for gaining an electron, so in this case, it turns out that nobody wants to gain an electron more than chlorine. So chlorine's like, if you give me an electron, I'd look like my idol, argon. I just want to gain an electron, just one. Let me gain an electron. And if you give chlorine an electron, he will release a ton of energy, more than any other element on the periodic table. And generally, the closer we get to these noble gases, so the more we would love to gain that electron, so to speak, and therefore it'll be more spontaneous and we'll release more energy in the process. So electron affinities get more negative as we go left to right across the periodic table. Now notice it does not include the noble gases in this trend. They're kind of an exception. They're like, no, don't give me one. I'm good. Chlorine wants one. I don't. Argon's like, leave me alone. I don't want your electron. I'm perfect the way I am. Don't mess with me. So, but chlorine definitely wants your electron. So we'll see there's some other exceptions in both of these trends here in a little bit. All right, so to see the exceptions for ionization energy in the trend, we'll call them irregularities in the trend here. We're going to take a look at all the period 2 elements, and I've kind of highlighted where the exceptions are in red here. And if you've got the study guide in front of you, you'll see entire columns with where these are located, highlighted in red. And so we see in general, though, you start from a low of 520, so for your ionization energy kilojoules per mole, all the way to neon at the far right, which is going to be at 2081. So the general trend says, yeah, ionization energy is going to increase left to right. Okay, so totally in line with what we know. However, we see that from beryllium to boron, rather than an increase, it actually decreases from 899 to 801. And from nitrogen to oxygen, rather than an increase, it goes down from 1402 to 1314. And so there's a brief reversal of the trend. Everywhere else, though, notice from boron to carbon, it goes up. From oxygen to fluorine, it goes up. Fluorine to neon, it goes up. So if you skip over nitrogen and go from like carbon to oxygen, it definitely goes up. And same thing here. If you go from nitrogen to oxygen, it goes down. But if you go from nitrogen to the next one over, you'd still go back to up. So it's just a brief reversal of the trend for the element right next to it, both between beryllium and boron, as well as between nitrogen and oxygen. And this continues on down the trend. It's not just beryllium compared to boron, it's also magnesium compared to aluminum and calcium compared to gallium, all reversals of the trend. Same thing, it's not just nitrogen compared to oxygen, it's phosphorus compared to sulfur and arsenic compared to selenium as well. And the truth is, there's also some exceptions to the trend right here, zinc compared to gallium, cadmium to indium, and mercury to thallium, that we don't usually present. They're on the study guide there and stuff like that because I wanted to be thorough, but it's not something you're usually going to be on the hook for in a high school chemistry class. All right, so let's talk about why this is, because this is a little bit strange and stuff like that. And we'll start with beryllium here. And so beryllium is 1s2, 2s2, whereas boron right next to it has an electron configuration of 1s2, 2s2, 2p1. And so it turns out, we know that the noble gases are happy. They've got a filled octet. That's a great place to be. Well, it turns out it's not the only good place to be. It's the best place to be for electron configuration, the most stable place, the lowest energy place. But there are two other good places to be. If you end your electron configuration with a filled subshell, like this guy right here, ends with 2s2, that's a filled 2s subshell, that's also got some stability to it. And as a result, it's going to make it a little harder to remove an electron from it because it's also in a good place. Same thing here if we look at boron. So boron, if you're like, he doesn't end with a filled subshell. He's like, I'm 2p1. But if you removed him from me, I'd end with a filled subshell, and I'd like to go there. And so nobody really wants to lose an electron, but boron's like, well, if anybody's got to lose one, how about me? So it turns out it's a little more complicated than just this reasoning. We can talk about shielding and screening and how the 2p electron is really shielded and screened by the 2s's a little bit. Even though we ignored it earlier, it really becomes relevant here. But I think that's really beyond the level of understanding you're going to need here. So suffice to say, though, that beryllium's in a good stable place. So if you fill up your s subshell and end there, fairly stable, harder to both remove an electron, and we'll find out in a little bit, also harder to gain one as well. So same thing for nitrogen. So nitrogen, it turns out, is not ending with a filled one, but it's going to end with a half-filled one. So if we take a look at nitrogen here, so nitrogen is 1s2, 2s2, 2p3. There are 3 p orbitals that can hold a total of 6 electrons. And we're exactly half full. And this is, you might think back to like chromium being one of the exceptions because it had a half-filled d subshell. Well, it turns out there's something special about having a half-filled. You get all those unpaired electrons that all have the same spin, which lowers the energy. And so he's like, I'm in a good place. don't take one of my electrons. We'll find out in a little bit with electron affinity. He also doesn't want to gain one either. He's in a good place. Whereas in contrast, oxygen here, 1s2, 2s2, 2p4, and now all of a sudden it's not exactly half full. It's one past that. He's like, though, if you stole one from me, I'd be half full. And it turns out, therefore, he's going to be easier to remove an electron from oxygen than it is to remove one from nitrogen. So that's how we kind of explain the trend. Either a filled S subshell in the case of beryllium, or a half filled in the case of nitrogen, or in the case of zinc, cadmium, and mercury, a filled D subshell in their case. Cool, so that's how we explain the irregularities in the trend here, and it turns out it's the exact same exceptions when it comes to electron affinity. So for electron affinity, we say that it's going to get more negative as we go left to right, but if you look at the diagram on your handout, it highlights where the exceptions are, and the exceptions are right back in the same place. Group 2, group 5 under nitrogen, and then also the noble gases are going to get included here because now we're trying to add electrons. Well, who doesn't want to gain an electron? Anybody who kind of likes the way they are. Well, if you got a filled octet, you're good the way you are. Not only did you not want to lose one, but you don't want to gain an electron either. Same thing with nitrogen's column, same thing with beryllium's column. They're all exceptions to the trend. And so if I give you an example here and a comparison, I say, compare the following. Who's got the most negative electron affinity? Well, let's say I give you lithium, beryllium, boron, and carbon as answer choices. You should look at this and be like, okay, as you go left to right, and maybe I'll write them left to right here actually, make this a little easier. The general trend, so lithium, beryllium, boron, carbon. If I give you this four and say, which one has the most negative electron affinity? Well, we know that generally they get more negative as you go left to right. So, but we should keep in mind, who are the exceptions? Well, the exceptions would include elements like beryllium. And it turns out if you're in group 2, so nitrogen's group here or the noble gases, you're going to totally defy expectations. Some of those don't even have negative electron affinities. They have positive values. All the noble gases do, nitrogen does. Some of these have positive electron affinities. They don't want to gain an electron. So, and some of them, even though they're negative, are not as negative as we would have predicted based on the general trend, or they're close to zero, and they're definitely fall out of line of the general trend. And so I'm just going to cross them off. If I want the greatest electron affinity, well, let's get rid of those exceptions. And so in this case, I would just pick carbon. So, however, if I threw the next element over, we'll also include not just carbon, but we'll throw nitrogen on the list. All of a sudden, I'd look at this and be like, oh, nitrogen's one of the exceptions. He's not going to have a very negative. In fact, he'll have a positive electron affinity. And so if I said, pick the most negative, but after I cross off the exceptions, pick the one furthest to the right on the periodic table, and we're going to pick carbon in this case. And that's the way we'd kind of run with it. So you got to know where those exceptions are. So, and unfortunately, both with ionization energy and electron affinity, you are more commonly going to get tested on the exceptions than on the general trends. Just the way it works. I didn't make up the rules. All right, so a couple other things we need to look at here, and that's what happens if you lose more than one electron and what happens when you gain more than one electron. All right, so we're going to look at successive ionization energy. So this would correspond to the energy for removing one electron. So, but what if we wanted to remove a second electron? So we already got a +1 charge because we already lost one, and now we're going to lose another, so we're going to end up with a +2 charge. Cool, well, it turns out that once you lose an electron and become a cation, because you lost an electron from your electron cloud, we just learned, your ionic radius is going to get smaller. And so if all of a sudden you get smaller, then when you go to try and remove another electron, it's going to be closer to the nucleus, and it's going to be even harder to remove. And so when you start removing successive electrons, they get more difficult. So if you look at the first, ionization energy is actually the entire trend we just learned, not for anything past that. So I put a few on here. So that first one we already saw was 801 kilojoules. But the second one on your handout there is 2427. I've got them in a table there. And let's get the third and the fourth up there as well. Okay, so if we look at the first four ionization energies for boron, we see that every time you remove an electron, indeed, it does get more difficult. First electron is only going to cost you 801 kilojoules per mole. Second one, 2427. Third one, 3660. It is definitely getting more difficult. But the fourth one, all of a sudden, you get a huge increase in ionization energy. Jumps all the way up to 25,000 joules. What in the world? Oh, sorry, 25,000 kilojoules. What in the world is going on here? So, well, it turns out if you take a look at boron, boron has how many valence electrons? Hopefully you said 3, based on where it's located on the periodic table. So it's got 3 valence electrons. So 1, 2, 3. And having 3 valence electrons, you can pull those off, and they are going to get more difficult as you go because it gets smaller and smaller and smaller. But once you run out of valence, now you got to try and pull off a core electron, which are significantly closer to the nucleus and therefore much more difficult to remove. And so this is kind of the thing you see. And so if I hadn't identified this as boron, but let's just say I called it element X, and I said, what element could this be? You'd look at the numbers here and be like, where's the big jump? And you'd be like, there's your big jump between 3 and 4. And that would be evidence that this guy right here has 3 valence electrons. And you'd say, it's probably like boron or aluminum. That's probably your most likely candidate somewhere. Somebody in that group that has 3 valence electrons. So that's kind of the way this works. And sometimes they'll present this graphically as well. So if we kind of take a look here. So we'll put ionization energy on the y-axis. And then we'll just kind of put the successive values there. So the first, second, third, fourth, and we'll see that, yep, ionization energy is definitely increased, but you get a huge jump in ionization energy once you run out of valence electrons. And so if you looked at the first, second, third, and then you see the big jump on the fourth, you'd be like, oh, yep, this guy's got 3 valence electrons. That could be somebody like boron or aluminum. Common question you might get is, which of the following has the highest second ionization energy? That's a little bit of a tricky question because that's not what the trend is for. The trend for ionization energy, we learned, was just for the first ionization energy. So how do you pick somebody who's got the highest second ionization energy? Well, you want to be sure and pick an element who, when it loses the second electron, is losing a core electron, not a valence. That way you already experienced that big jump. Well, if the second electron you lose is going to be a core electron, then you must have only had 1 valence electron, and you must have been one of these alkali metals. So the alkali metals tend to have very high second ionization energies because by the time you go to remove that second one, they've already lost their only valence electron. So a little bit of a tricky question, but that's usually kind of where they're going. Now, if we look at successive electron affinities for a second as well, so oxygen again gaining 1 electron. And now let's have oxygen gain a second electron. And let's put the numbers on there as well. Let me flip this over. So we got negative 141 and positive 744. So I already learned that not everybody wants to gain an electron. So we learned that beryllium's column, nitrogen's column, noble gases, they don't want to gain an electron. But what we're about to learn is that nobody wants to gain more than 1. So because once you gain more than 1 electron, and we should have oxygen with a negative charge here to start with. Once you gain 1 electron, you've got a negative charge. And if you're negative and an electron's negative, then the net force operating between you is a repulsive force, and you don't want to gain each other. You don't want to be near each other. And so if you're going to gain that second electron, it's going to actually cost energy instead. So gaining 1 electron, most elements want to do that, and we know the exceptions that don't. But gaining 2, nobody wants to actually gain 2. And you might be like, wait a minute, Chad. Well, I know that oxygen likes to gain 2 electrons. He likes to gain 2 so he can look like a noble gas. Well, that's kind of how we say it, and we're kind of lying. Nobody actually wants to gain 2. It turns out there are other benefits when he's involved in forming compounds of why he might gain 2 electrons. But it turns out he doesn't actually want to gain the second one. He wants to gain the first, but it's going to actually cost energy to gain the second. But the reason he does is that the energy cost of gaining that second electron will be more than made up for when he actually participates in ionic bonding. We will get there actually in the next chapter, I believe. We'll talk about ionic bonding a little bit and find out why in the world he'd want to gain that second electron. So it's an investment. He invests a little energy here, more than will be paid off for when he starts forming ionic bonds. Cool. These are your periodic trends, though. Again, atomic radius, ionization energy, and electron affinity. We've gone through the trends and the reasoning behind the trends. We've gone through all the exceptions, which are really important and commonly tested upon. And we've also gone to different places where where you might be on the hook for applying these things. So you definitely want to get good at this. You definitely want to spend a little time with this. I'd highly recommend, downloading the study guide here and working some problems with it handy so that you can kind of get down where those exceptions lie and stuff like that, and eventually just kind of phase out using them so that you can work out practice problems without having them handy. But you definitely need to know where those exceptions lie. Now, if you found this lesson helpful, would you consider giving me a like and a share? It's a couple of the best things you can do to support the channel. And if you are looking for the practice problems that go with this, or if you're looking for the study guide that went with this lesson as well, check out my premium high school chemistry course on chadsprep.com.